Hey, welcome to another video. So we've just explored what the logistic equation was. We've explored what extinction and doomsday looks like. We've explored what bounded growth and unbounded growth looks like for populations, in other words. We did a lot of theory, and we are going to get to, in the next videos, how to work with that logistic equation and what sort of problems are modeled by it, and how to work with explosion and extinction of populations. But before we get there, I thought it'd be really nice to give you some introductory problems on how you go about thinking of some of these setups, because stuff like this isn't necessarily modeled exactly by the logistic equation. This is not that advanced, but it's going to step up to it. So we have a real good feel with how population works, hopefully. Now it's time to look at some real examples to get maybe an exploration on setting up some word problems again, because sometimes it's really hard. And so I'm going to show you how that works. I'm going to do just two examples. Then next time we'll start looking at more of the logistic equation, and then we'll talk about these population explosions that we could have. So, and I'm going to do that on the second example we covered today. Just think about what would happen a little bit later. We'll see why this is. So let's look at one example. Let's say that there's a squirrel population, and the rate of change of the squirrel population is proportional to the square root of the population itself. So what does that mean? It means that the way that the population is changing is directly related to the square root of the population itself. And we're gonna look at how this affects the outcome of our problem. Remember that one thing we were very interested in the last video is this population bounded or unbounded? We'll start thinking about that as we go through. At time zero, when you first start looking at it, there's 100 squirrels, and it's increasing. It's 20 squirrels a month. That's a lot of squirrels. How many squirrels will there be in 1 year? So we're going to diagnose exactly what this does. So firstly, the time rate of change of a squirrel population. What in the world is a time rate of change? That is the rate of change of a population with respect to time. So, okay, well, if we make P the population, then the rate of change of our population with respect to time, let's see, is proportional to. When you hear that word proportional to, that means that you have a constant being multiplied by some variable. So if the rate of change of our population with respect to time is proportional to, that's going to be constant times, proportional to the square root, not the square root of our population. Notice something, this is a very stripped down problem. There's nothing about how birth rates are changing. There's nothing about how death rates are changing. All this is giving you is some very basic information like, okay, the rate of change of our population is proportional to the square root of our population. But it's important to be able to set these things up. Now, the next statement says, all right, at time equals 0, there are 100 squirrels, and the population is increasing at a rate of 20 squirrels per month. Let's think about that for a second. So, the population at time 0 is 100. So the initial population is 100 squirrels. But then this is really weird. It's increasing at 20 squirrels per month. Well, wait a minute. We know that increasing things that are increasing or decreasing, things that talk about a rate of change are talking about that derivative. So when this says this is increasing at 20 squirrels per month, what's increasing? Well, the population with respect to time. Whoa, that's talking about your derivative. So this is saying the population is increasing with respect to time at a rate of 20 squirrels per month. Now this happens at a certain point. So this says at time equals 0. Okay, so right when we start, we've got 100 squirrels. No problem. I have 100 squirrels. But the population is also increasing at 20 squirrels per month. So the first derivative of population with respect to time, the way that our population is changing with respect to time, this is increasing at 20, so positive 20 squirrels per month when t equals 0. Here's what this means for us. What this means is with some of these basic examples, we can plug in everything and solve for that constant. If you remember back to like the early days of the idea of populations, one of the big ideas was solving for that constant. We did that with like half-life. We did that with other sort of radioactive decay or population increases exponentially is we wanted to find out what that constant of variation was, so that k in other words. So one time all the way through, we read our problem and go, all right, the time rate of change is a derivative. It's the way that the population is changing with respect to time. We know that that's proportional to, so a constant times the square root of the population. Great. But then we get to some other information. At time equals 0, we have two things going on here. We have that the initial population is 100. Fantastic. We also have that the change in population with respect to time is 20. That's at time 0. What that means is that we can plug in the 20 and the 100 and we can solve for k right now. So at time equals 0, notice how this and this match up. So they're both at time equals 0. We can say that at t equals 0, our population with respect to time is changing at a rate of 20 squirrels per month. And there are 100 squirrels present. We're going to get k equals 2. So that's kind of nice. Because that lets us change this original differential equation into something that doesn't have the arbitrary constant, or that constant in it, sorry, that constant variation in it. One thing I want to mention right now, this is the most basic example that I could find, okay, or come up with. Later on, it's not going to be that simple, and so what we're going to be doing is, it's not always going to give you this right there. It's not always going to tell you the rate of change of your population with respect to time right off the bat. So when that happens, you're going to have that k in there for a while until we start integrating. So now we go, okay, well, hey, our rate of change of population with respect to time is, we had the constant of variation, but now we know it's 2 square root of p. And this looks a lot better because this is something that's a differential equation that's separable. And we can solve that, man, not too bad. Do you remember that? That we have a differential equation, it's respect to time. So we're going to move our p's, dp, our constants dt in this case, our independent variable is t. So we'll have this 1 over the square root of p dt equals 2 dt. And let's take an integral on both sides. On the right-hand side, we have something nice. We just have 2t plus some sort of arbitrary constant. On the left-hand side, we have this, well, you might want to think about this as p to the negative 1/2. So let's see, with that, we're going to add 1, that's p to the 1/2 over new exponent 1/2. That's 2 square root p. You might want to do this on your own. P to the positive 1/2 over 1/2. So I'm going to give you 2 square root of p. Now, what in the world do we do after that? Well, it's probably a good idea to solve for p. I think we've done that many times before. So if we go ahead and we start solving for p, let's see. Square root of p would be divide by 2. We get this t plus c over 2, not a problem. Maybe we square both sides. We could do that. But we do notice something that's up there right now. We notice that there's a constant there. And if you remember, before we get too heavy into this, it might be a good idea just to solve for c right now. We did that even in the last video with that crazy hard stuff. We solved for the constant, the arbitrary constant first. Wait a minute, how am I supposed to solve for that arbitrary constant? Because this tells you the initial value, you can always use that to solve for your arbitrary constant. We did it basically in every population problem we've ever done. So I might go back and say, you know what, I don't want to do that, because if I solve this for p right now without getting that arbitrary constant, I'm going to have to go backwards. So let's take this and say the initial population at time 0 is 100. Let's put that in. Let's say that our population is 100 when our time is 0. And we're going to get, let's see, 2 times 10 is 20. C equals 20. This is going to give us something a lot nicer, because when we solve for p, we'll be done. We won't have to go back and solve for that c again. So let's rewrite this. 2 square root p equals, now we know that's 2t plus that arbitrary constant is no longer arbitrary. This was an initial value problem. It told us the initial value was 100 squirrels. And now look how much nicer it is. When we start dividing by 2, we can get a constant that we know, understand, and don't have to solve for again. So we're going to get we're going to get t plus 10. And if we square both sides, we'll get that the population with respect to time is given by this equation, t plus 10 squared. So let's see, we looked at it, we read it very carefully. We wrote down exactly what a time rate of change means. We wrote down what proportional means. We wrote down what a square root of p means. We wrote down an initial value problem. We wrote down that increasing is relating to that rate of change. It's saying what the rate of change is. We were able to solve for that constant variation. We did our integration. We were able to solve for the function p, our population p. We also were able to get rid of the arbitrary constant by using the exact same initial value, that p of 0 equals 100. And now we have a formula for that population of squirrels. So now we can answer this last question. And the way we do it is say, okay, well, how many are there in 1 year? It's almost always this case where they're going to give you a time, you find the population, or they give you a population, you have to find the time it takes to get there. So in this case, it says, I'm giving you 1 year, how many squirrels are there going to be? So the population of 1 year, well, wait a minute. Oh, junk. This is 20 per month. So 20 per month, but I'm giving you 1 year. Is this going to be accurate if I put in 1? Is that going to be accurate? Is the time unit the same? The answer is no, it's not. Be very careful. If you're getting the wrong answer in the back of the book and you're going, I'm plugging in 1, man, I followed you, Leonard, and well, it might be that we're plugging in different units of time. You see, if our time rate of change is based on months and they're giving you years, we have to realize that 1 year is 12 months. So I'm not going to be plugging in 1, I'm going to be plugging in 12. That's going to give us something quite different. So when we look at it, we go, right, let's see, that would be the population after 1 year, or 12 months, is 22 squared. Looks like I got 484 squirrels. So when we look at it, start thinking what would happen if our time did increase a lot. And we found out how many squirrels there are in, man, 20 years or something. Is there anything here that's going to slow that down? Is there anything here that says after a certain amount of time or based on the population, we're going to be reaching a plateau or a valley? Or are we going off the scales, or are we dropping down to 0? And if we look at this, basically no matter what our population, initial population is, check it out. No matter what our initial population is, if it's positive in any way, shape, or form, then this is going to be a positive number, this is going to be a positive number, and this is going to be a positive number. So we would have some sort of positive constant. We'd solve for p. This would be some sort of time plus a positive constant squared. Well, as this goes further and further and further, if this gets increasing to infinity, this is going off the charts. This would be a population explosion. So there's nothing that's limiting this. We don't even have really a threshold. The threshold would be like 0. The only way that you would go to extinction is if you didn't start with anything here. So if you started with a 0 population, then yeah, our constant would be 0, but there'd be nothing to start with. So there's no way that we could ever increase. That wouldn't even make sense. But if we start with any population at all, and we say this is what's happening here, just an arbitrary increase at 20 squirrels per month, then we're going to be increasing forever. There's nothing that's going to really make this not go to infinity. It's increasing without bound. So let's look at the next example. All right, so last example for this video, just again to get our feet wet, just understanding how to set these problems up even. Let's talk about rabbits. You know what rabbits do. So the time rate of change of a rabbit population is proportional to the square of p. What's that mean again? The time rate of change is this rate of the population with respect to time. So we're talking about a derivative here. At time equals 0, so whenever this was studied, there was 12 rabbits, and then there was 24 rabbits in 10 years after that. when will there be 48 rabbits? And then we're going to talk about like what I want you to get. And the last video and this video is what's going to happen in the future. Is this going to climb without bound? What's going to happen after that? Okay, well let's talk about it. So let's try to diagnose every bit about it. We'll put it together, do our integration. We'll learn that we can't solve for that k right off the bat. We'll see why that is. So the time rate of change of a rabbit population is proportional to the square of p. What that means is that the way that the population is changing with respect to time is proportional. That's a k times the square of p. So not the square root, but we're going to have k times p squared. And we're going to see how this really affects the integration compared to the last problem. Also, look for this other stuff. Is there an initial value? At time equals 0, are there an initial number of rabbits? Yeah, 12. So when there's the start of this problem, there are 12 rabbits altogether. Let's look for this. Is it telling you how the population is increasing at that time? No, it's not. Is it giving you another value? So we basically need two of these things, one to solve for our arbitrary constant and one to solve for our k, our variation coefficient. So, man, it's not telling us this. It says that there's 12 at the time equals 0. It's telling you there's 24 10 years after that. Oh, so it's giving us another value. So when we're looking at this, we're trying to identify what they're giving you. They're giving you a derivative of population with respect to time. They're giving you that it's proportional. That's a k times. They're giving you that it's the square of p. Okay, that's p squared. They're giving you an initial population of 12. They're giving you a population some time period after that. Starting to sound very familiar to what we've done already. So after 10 years, the population has doubled. Let's go ahead, and since we can't solve for that k right now, since we don't know that's the problem. In the previous example, we knew what the rate of change was. We don't have that now. We're going to have to find it by doing a derivative, our integration, doing our separable variables here, doing our integration, and then we'll have to find out a little bit later. So let's start that. Let's say, hey, that's a differential equation. It is separable. Let's group our p's dp, our constants dt. So if we divide everything by p squared dp, leave our constants dt, and when we integrate, let's see what we have. We have an integral of p to the negative 2. Let's add 1, it's negative 1. Divide by the new exponent, that's negative 1. That's negative 1 over p equals kt plus some sort of arbitrary constant. That looks kind of nasty. Let's fix this a little bit. Let's go ahead and let's multiply everything by a negative. So 1 over p equals negative kt minus c. Do you really want to deal with that minus? I don't really want to deal with that minus either. Also, one other thing that we could do this right now. We could wait a little bit. We could solve for that constant, couldn't we? So typically what you've seen me do is before we start doing things like, man, let's multiply both sides by p, divide by this, or just reciprocate and get this is 1 over arbitrary constant minus kt. I'm saying that this could be written as positive c. Just call this c sub 1, and then that would be a positive c. You could do that, and you could solve for c. But do you see how much time? You'd be wasting right now? If you're going to solve for the arbitrary constant right now, you're going to have to undo basically all that work you did. So I'm showing you this to say when you do your integral, and we've seen this from one of the first sections we did. It was a long time ago, like 30 videos ago. But from one of the first sections we did. As soon as you do your integral for integration by parts, if you have an initial value, it will solve for your arbitrary constant. It won't solve for k, but it will solve for your c. So here's the process going through it. Read your problem very carefully. Get your differential equation, write down every piece of information that you know, see if you can solve for that k. If you're given the rate of change, you can. If you're not, then the process is do your integration to solve your differential equation. As soon as you get this arbitrary constant, as soon as you do your integration and you get that arbitrary constant, it's easiest to solve for that now, and it's always solvable by your initial value. So this guy. Then after we solve for our constant, we can use this, the second piece of information, to solve for your constant of variation. So again, do your integration, solve for your arbitrary constant, your c, by using your initial value problem, and then solve for your k by using the other piece, the what happens later. We'll solve for that k for you. So let's do that. Let's say, hey, you know what? When our time was 0, we had 12 bunnies. So -1/12 equals, this whole thing's 0. That's why we use the initial value to solve for c, because the time zeroes itself out, equals c. So our c is -1/12. Let's rewrite that. So plus -1/12 minus 1/12. Now what now? Well, we just mentioned that if we use our initial value to solve for our c, we can use the next piece of information to solve for our k. So we're going to do that. We're going to say that now that we know that after 10 years, there were 24 bunnies, says we can plug in 24 for p when we plug in 10 for t. And after having solved for that c, it leaves us just one more variable. So -1/24 equals k times 10, or 10k, minus 1/12. Let's go ahead and let's add 1/12 to both sides. So if we add 1/12, let's see, that would be 2/24. We're going to get 1/24 equals 10k. And if we divide both sides by 10, we're going to get k equals 1/240. Might not look that great, but at least we don't have two constants any longer. We don't have our arbitrary constant. We know that's -1/12. We don't have our k anymore. We know that's 1/240. So what we're going to do is, after we've done our integration, we solve for our arbitrary constant. No longer arbitrary. Use initial value for that. We solve for our constant of variation. We now know what that constant is. We're going to rewrite this right now. So we found c, we rewrote it. We found k, we're going to rewrite it again. Now, before we go any further, we're about to reciprocate this. You can't reciprocate two fractions. You can't do that when they're being subtracted or when they're being added. So we're going to take the time, we're going to make a common denominator, and we're going to make this one fraction. So let's see, -1/p, and then on the right-hand side, this right here, let's see, 1/12, and I'm trying to get 240 to be multiplied by 20, so 20/240. So t minus 20/240. You know what we're going to do now? Let's change that side. I don't like that. Let's multiply both sides by a negative. So -1 or divide by a negative, doesn't really matter. So 1/p is going to give us, if we multiply both sides by a negative, let it just affect the numerator or denominator, but not both. So on the numerator, we'd get positive 1/p here, but we'd get -t plus 20, or 20 minus t. We're just reversing that, changing the signs, over 240. And now we can reciprocate both sides. So our population with respect to time, and that time is in years, so we're having that in the back of our head. Time is in years, is 240 over 20 minus t. And now it asks the question, says, all right, hey, can we answer this now? I told you last time that when you get down to your population, so solving your differential equation, you got your population model, and it's going to ask you one of two things usually. It's going to say, well, how much of what quantity, what's your population after a certain time, or how long does it take to get to a certain population? And that's what this one says. When will there be 48 bunnies? Well, a when is what's the time? The 48 bunnies is what's your population? So if there's 48 bunnies, how long did it take to get there? It's a matter of solving for t now. So you multiply both sides by that 20 minus t and divide by 48, or if you remember, this is that can be used as a proportion. You can cross multiply, no problem. Me personally, I like doing that whole switcheroo thing. Like if you were to multiply by 20 minus t and divide by 48, you'd get 20 minus t equals 240 over 48. And then if we subtract 20, so 40 minus 28, that's 5. When we subtract that 20, we're going to have 15, but negative 15. Oh, good thing we divided by negative. So t equals 15. Now we think about the units. This was 15 years. Everything was in terms of years for us, which was nice. So in this case, these are some slow producing bunnies. But if this is true for this population, maybe there's heavy predation, maybe it's not growing that rapidly. But what's going to happen here is that this population is going to grow and grow and grow, and to the point where we have 48 rabbits in 15 years. Now, this is what I want you to get out of this too. What's going to happen first, I hope I've explained this one for you, that you understand how to set these word problems up. But the idea in the last example was, what are we getting out after this? What is this population going to do? And I want you to look at the time. Look right here. What happens as we get closer and closer to 20 years? So as we get closer and closer to 20 years, well, let's see, that denominator gets smaller and smaller and smaller and smaller and smaller and smaller, doesn't it? So 20 minus 15 would give us 5 after 48 bunnies. How about 20 minus 19? What happens in 19 years? Well, in 19 years, we got 240 divided by 1. That's 240 bunnies. So in 4 more years, this is going to really start, that 48 is going to start exploding. What about in like 19.9 years? That's going to, let's see, 20 minus 19.9 is 0.1. 240 divided by 0.1 is 2,400 bunnies. So it took a long time to get there. This is very slow growth at the beginning. Man, I don't know anything that starts off growing really slow and then just starts exploding like that. I don't know anything that looks like that. That's because that's exactly what this is. It's crazy fast growth is what this is doing for us. So somehow we are going to be starting off super slow, but at some point we are going to be exploding. As this gets really close to 20 years, this population starts really getting crazy, crazy big. To the point where it's reaching infinity. We can't even go any. You can't actually get to 20 years. It's undefined. It's going so fast. It's undefined. That population is a doomsday population. What that means is that you've reached such a expansive population. There's not even room for it anymore. Like it's infinity. This approaches 20 years, this is going to approach infinity. Do you see it? Are you seeing that? If this approaches 20 years, so this approaches 20, this is getting really close to 0, 240 divided by something really close to 0 is going to positive infinity. From the left-hand side, it's going to go to positive infinity. That's a doomsday situation where this population is getting so big, there's not even room for it. There's definitely not food for it. So I hope that makes sense. I hope that I'm teaching you to think about what's going on, not just answering the question. The answer to the question is 15 years, but what's happening after that's important. We have talked about the logistic equation. We've talked about the extinction versus explosion. That's an explosion idea. But now we're just getting some basic concepts. I'm trying to mirror what we've already learned in the last video so that later on, when we get to those examples, you're much, much better suited to deal with it. So I hope this makes sense. I hope now you have a great way to start setting up some word problems and are understanding what can happen in these explosion ideas right now. So we'll talk about more of this next time. We'll get heavy into it with a logistic equation in a little while. Okay, hope you enjoyed it. I'll see you for the next video.